Hi everyone, my name is Raymond. I'm a postdoc at the University of Minnesota. Today I'll discuss the recent development of axion physics. We discovered that the unexplored dynamics of the axion in the early universe can give rise to dark matter, baryon symmetry, and potential signals of gravitational waves. In this talk, I will focus on the initial condition shown in this one-body potential, labeled by the number 2, and this initial condition and the dynamics following this condition can give rise to dark matter, the baryon symmetry, and potential gravitational wave signals. But let me give you the punchline figure first. This is the usual axion parameter space, where the y-axis is the coupling between the axion and photons. The horizontal axis is the axion mass. The yellow band is the QCD axion prediction. The gray band is the prediction if you want axion dark matter to come from the conventional Meissner mechanism. In our scenario, if we want to produce both dark matter and the baryon symmetry, we have to live in this blue region for the QCD axion and in this green band for the axion-like particles. Let me first define the notations. Here, what I'm showing is the one-body potential of a complex field P that breaks the Pacheclian symmetry. Specifically, there's a radial mode and the angular mode. The angular mode is the axion. The radial mode, we don't have a specific name for it, so we call it the saxion to borrow the language from supersymmetric axion theories, even though we don't always have to assume supersymmetry. When the temperature is still larger than confinement scale, the axion is massless, but when the energy scale drops below it, then the axion picks up a mass from the QCD effects. Here on the left, what has been considered in the literature is that the saxion can be sitting at the origin or the minimum or at a large field volume. And the dynamics that follows could be the radial oscillation in this one-body potential. What we consider in this talk is that the saxion not only can start with a large field volume, but it can actually experience an angular motion in the axion direction, which means that the motion is not going to be a radial oscillation, but more like a spiral motion if you take into account the effect of redshift. So let me motivate why the saxion can take on a very large field volume initially. So the idea is that you can think of it as an initial condition, or there's also that a dynamical reason why the saxion could be starting with a large field volume. The idea is that the saxion can couple to the inflaton, and the inflaton would produce the so-called Hubble-induced mass to the saxion. And if this Hubble-induced mass is negative, then the mass becomes tachyonic, then the saxion will be driven to a very large field volume, which will be further stabilized by a higher dimension operator. So now that we start with a large field volume, why do we expect angular motion? The idea is that the conjecture in quantum gravity is that quantum gravity does not respect a global U1 symmetry. What it means is that there's always a higher dimension operator that breaks the U1 symmetry. In this case, this higher dimension operator will give a mass to the axion. This is the source of the axion quality problem, where you don't want the explicit PQ breaking term to give an axion mass that's too large to spoil the solution to the strong CP problem. So the usual solution is that you can model build to make this dimension n to be large enough so that the decay constant of the axion divided by the cutoff scale to a high power is suppressed enough. However, in our case, this is not negligible, especially in the early universe. The idea is that when the P is driven to a very large field volume, stabilized by higher dimension operator, naturally, you'll find that the P will be very close to the cutoff scale of the theory, which means that even if this is a high power, this initial field volume over the cutoff scale may not be small. In that case, it will lead to an axion mass from this explicit breaking terms. And that's what you see in the wiggles of the potential. When the field volume of the saxion is large enough, then the axion experiences a mass. Unless you're unlucky that you're starting from the minimum or the maximum of those wiggles, you will actually expect to have an angular motion. And this whole dynamics of the initiation of the rotation is analogous to that in the F-like-line baryogenesis. Let me give you a different understanding of the rotation. Since in this case we have a shift symmetry, then there must be a conserved quantity. If you use the Noether charge computation here from the complex field P, you'll find that the number density of this conserved charge is given by S squared times theta dot. S is the radius, the Saxion field value. Theta dot is the angular speed in the Axion direction. And this is not surprising because the shift symmetry here is nothing but the rotational symmetry in the classical sense. And the conserved quantity is angular momentum. And this is exactly the formula for angular momentum, R squared omega. So soon after the onset of this motion, when the higher dimension operators become inefficient, when the field value drops, then this PQ charge is conserved. So we call this conserved charge PQ charge or the PQ asymmetry. But what is important here is that this quantity is conserved soon after the onset of oscillation. And now I would explain to you why such a initial condition will actually lead to a large angular speed at low temperatures that would be relevant for dark matter and baryon asymmetry. So we have argued that this number density should be conserved up to the expansion, which means that n times r cubed should be the total charge and it should be conserved. In the conventional evolution, where the Saxion is not at the large field value but at the minimum of the potential, then the Saxion field value is fixed at Fa. Then from this scaling, you can tell that theta dot has to scale as r to the minus 3. So in the conventional understanding, this initial velocity, even if you initiate it somehow at the minimum of the potential, will redshift very quickly. But in our case, since we start with a very large field value, the field value of the Saxion redshifts depending on the potential of the Saxion. It can be a quartic potential or quadratic potential. But in any case, when you find the redshift of the theta dot, you find that the redshift is significantly slower than the conventional case. And this could be the reason why this scenario has been overlooked in the literature. So now let me discuss the implication for dark matter. The idea is that when the rotation is very fast and it is preserved to low temperature, then this axion will be running at the minimum of the potential very quickly, maybe even during the QCD phase transition. In that case, what determines the abundance of the axion at the end of the day is not the misalignment angle as in the conventional misalignment, but the initial kinetic energy. Another way to see is from this video. The blue dot is the conventional misalignment mechanism. When the Hubble is comparable to the mass of the axion, the axion starts to oscillate, but at this time, the axion may still have a very large kinetic energy, and it may come in at a much later time, and it starts to oscillate only when the kinetic energy is redshifted enough so that it cannot overcome the last potential barrier, and the oscillation will start. In this case, the net effect is that we delay the onset of oscillation, and the oscillation will begin with the maximal misalignment angle, pi. So at the end of the day, this kinetic misalignment mechanism would enhance the axion dark matter abundance. So we have built some models to show open parameter space, but what is important here is that we're able to explain axion dark matter in the region where conventional misalignment mechanism will underproduce axion dark matter. So far, we cannot make a prediction because it depends on the initial speed, or another way to say that is that it depends on the initial PQ charge. However, we can think about other observables that we can connect to make a prediction. So in this parameter space, the idea is that you would have kinetic misalignment mechanism at play if you're above the gray band, so that you can still produce enough axion dark matter. Next, I would like to discuss the connection with baryogenesis. In this case, we call it the axiogenesis because we're using the QCD axion to do the job of baryogenesis. And what is specifically exciting about this scenario is that we're able to explain all three symmetries of the universe simultaneously. The first mystery would be the strong CP problem that's explained by the usual QCD axion. And now we're able to explain both dark matter and the baryon symmetry from this rotational motion. So the basic idea is that, as we discussed, the rotation corresponds to the PQ charge asymmetry. The question now is that how do we transfer this PQ charge asymmetry into the baryon asymmetry that we observe in the universe? And for the QCD axion, by definition, it is anomalous under SU3, which means that the strong phaleron will actually transfer this PQ charge asymmetry into the chiral asymmetry of the quarks in the standard model. And the chiral symmetry of the quarks will further get processed by the standard model electroweak phaleron processes into the baryon asymmetry. Another path is that if the PQ charge or the PQ asymmetry is anomalous under SU2, then the electroweak phaleron process can also directly transfer this PQ charge asymmetry into the baryon asymmetry. The estimate of this baryon number density is given by theta dot times t squared. Whenever this process is in equilibrium. The question is, when do we evaluate this baryon asymmetry? The answer is the electroweak scale, because once the temperature falls below the electroweak scale, the baryon asymmetry is frozen by the ineffective electroweak phaleron processes. So the yield of the baryon asymmetry would be related to the PQ charge asymmetry and also the electroweak phase transition temperature, as well as the decay constant. If we think of this as a way to fix the PQ charge asymmetry from a given decay constant, then we can use this to predict the dark matter abundance. Here, this is the formula to show you the size of the PQ charge yield. If I fix the decay constant to be 10 to the 8 GeV and the electroweak phase transition temperature to be the one predicted by the standard model. In this case, the YPQ has to be around 500. And we can use this one to figure out whether we under or overproduce axion dark matter from kinetic misalignment. And the answer is that we overproduce this by a very little bit. If this number were consistent with 1, I would have totally called it the Axiogenesis miracle. However, life is never what you expect. So the question is, what else can we say about this equation? What predictions are we making? The answer is that it is possible that we're actually making a prediction of the electroweak phase transition temperature, because we don't actually know what this temperature is. This 130 GeV is just a prediction of the standard model. So if I want to fix this number to the observed value 1, then we're making a prediction of the electroweak phase transition temperature as a function of the decay constant. And here we show some parameter space that's open to produce both the axion abundance in dark matter and also the baryon asymmetry. But I won't go into the details of the plot. So what is important to see from this plot is that the decay constant that's required is relatively low. For example, 10 to the 8 to 10 to 10 GeV. And that corresponds to this region in the parameter space. So now the next question would be, what if I don't consider the QCD axion? What can we say about the prediction? So by definition, we cannot have a strong phaleron for axion-like particle, but we can still have the electroweak phaleron processes that help us transfer the PQ charge asymmetry into the baryon asymmetry. And the formula will be given by exactly the same thing, except that this estimate of the order 1 coefficient will be slightly different. Now it depends on the coefficient of electroweak anomaly. The prediction, if you put in numbers, would be the green band here. This is what we call the ALP cogenesis. As you can see, this ALP cogenesis will intersect with the QCD axion band in the region that is already excluded. So that's what we saw in axiogenesis, where we have to use a different, meaning higher electroweak phase transition temperature to achieve both abundance. And that's in the axiogenesis region. But if we're using the axion-like particle, then we can live in this green band. And this green band is especially exciting because it is predicting an interaction strength that's stronger than the conventional predictions from the gray band and the yellow band. This is a similar plot, but for the axion coupling with the nucleons. The Casper experiment can probe light axion regime for our predictions. This is the plot for the axion electron coupling. The future experiments Axion and the current experiment CASP can also probe into these regions. what if I don't want to raise the electroweak temperature of the standard model? Is there any other way to help us revive the scenario? The idea is, how do you transfer the peak charge asymmetry into the baryon asymmetry more efficiently? Then the answer is to look for other baryon number or lepton number violating processes. It turns out that the neutrino mass may play a role here. It is possible that we can use the Majorana neutrino mass term, which is this dimension 5 Weinberg operator, whose coefficient is fixed by the neutrino mass and the electroweak VEV. And this interaction violates the lepton number. In that sense, we can actually generate the baryon symmetry in a different route. So here's the diagram that will show you the idea of the transfer. This first part is the same as before. Now we have the quartile symmetry. They can be reprocessed to produce the Higgs number asymmetry or the lepton asymmetry by the standard model Yukawa couplings and the electroweak-Faleron processes. And what is important is the next step, that this Higgs number and the lepton number asymmetries can be processed into the lepton asymmetry from the dimension 5 Weinberg operators. And this would eventually be transferred to the baryon symmetry from the electroweak-Faleron. And what is very interesting in this case is that because B minus L is conserved by the electroweak-Faleron, the way we can imagine is that this first box is producing the lepton number asymmetry at a very high temperature. And this lepton number asymmetry gets reprocessed into the baryon symmetry at very low temperature, the electroweak scale. The end result is what we call leptoaxiogenesis, and it is making prediction of a decay constant that is also relatively small, which means that the axion mass has to be large in the QCD axion band. But what we have shown so far is that the QCD axion is able to produce the dark matter abundance and the baryon symmetry with the rotational motion. The last part of the talk, I will talk about the additional ingredient, which is the axion coupling with the dark photon. And my claim here is that with this coupling, we can actually produce observable gravitational waves and or dark photon dark matter if the axion is not dark matter. So the idea is that here you have an axion coupling with the dark photons. This is going to modify the equilibrium motion of the dark photon. Specifically, you will add this term to the equilibrium of the dark photon, and this term depends on theta dot. In our case, our theta dot is given by the explicit breaking. From the equation, you can see that there are two modes of the dark photons. One of the modes would become tachyonic if theta dot is large enough, because then this term will be negative, and theta dot, as we have seen before, does not redshift quickly and stays a constant even for the quadratic potential. In that case, then the dark photon is tachyonic in mass, and that means the solution of this equation will be an exponential. And what that really means physically is that we're transferring energy from the rotation into the dark photons. And what that implies is that you would create a large energy density in the dark photon with a specific momentum mode. And that momentum mode is given by the tachyonic mode. And that would source the fluctuations in the space-time. And that would in turn lead to gravitational waves. Here's the probability space for the gravitational wave as a function of frequency. We check at various points whether we can have a model that provides a consistent cosmology. And it turns out that it is possible for all of the points that we have checked. Specifically for the nanograph tentative signal at this point, we also have some open probability space. And lastly, to produce dark photons can themselves be dark matter if, again, we're assuming that the axion is subdominant in dark matter abundance. In that case, since the dark photons are produced with a specific momentum, they can be warm today. So we're making a prediction between the warmness of dark matter and the strength of the gravitational wave that we observe. We also check some probability space in here to see if the model has some open probability space, and it does. All right, here comes the conclusion. I hope I convinced you that the new axion dynamics allows the QCD axion to explain the three mysteries. The first one is the strong CP problem, the second one is the dark matter abundance, and the third one is the baryon asymmetry. That if the axion couples to the dark photon, then we can produce, for example, observable gravitational waves and or dark photon dark matter. The axion we produce from kinetic misalignment mechanism could also lead to warmness of the dark matter. Thank you very much for your attention.